29.50. Suppose the loop is rotated about the y-axis, part B rotated about the x-axis, or part C rotated about an edge parallel to the z-axis. What is the maximum induced EMF in each case if the area is 600 centimeters squared, omega is 35 radians per second, and B is 0.32 Tesla? Okay, so our EMF is minus d by dt of the magnetic flux. So for part A, when we're rotating about the y-axis, that's exactly how it's drawn in this picture here. So we're going to be going this way. So if you remember, our flux is B dot A. So in this case, A is initially pointing, or it's pointing perpendicular to the surface. So when we start, A and B are parallel to each other. As this starts rotating, this area vector starts sweeping out. So if you kind of visualize, it's going like this. So we're going to call this an angle phi. So this dot product becomes B times A, and then in order to keep our area vector parallel to B, that's going to be cos phi. So this angle phi can be described in terms of our angular velocity. Just like distance is velocity times time, angular distance is angular velocity times time. So we can write this as BA cos of omega t. So our induced EMF is going to be minus d by dt of BA cos omega t. So B and A are constant, so we can pull them out. Oops, forgot my minus sign. Minus B and A, constant. Derivative of cosine is minus sine omega t, and then chain rule gives me an extra omega. So it's asking about the maximum induced EMF. So the maximum EMF is going to be when sine of omega t is equal to 1. So our max EMF is going to be B times A times omega. So that's our 0.320 Teslas. Our A is 600 centimeters squared, but we need to convert that. So there are 100 centimeters and 1 meter, but you have to do it twice because it's centimeter squared. And then times our omega, which is 35 radians per second. So if we punch that into our handy dandy calculator, we have 0.32 times 600 divided by times 35 divided by 100 squared. So that's 0.672 volts. Okay, so now let's look at part B. So part B is rotated about the x-axis. So if we rotate it this way, our B field is and our A is always going to be parallel to each other. The area that is being exposed to the B field is not changing. So let me find a nice rectangular thing. So it's like my calculator is the surface. My B field is coming out. As I spin this calculator, the flux through that area remains constant. So there's no EMF that's going to be induced. So my flux is constant. So EMF equals 0. Alright, so for part C, we're rotating about an edge parallel to the z-axis. So now we're taking our dude, we're pinning him here, and we're spinning him that way. So now, instead of rotating up and about our area vector is going to be swooping along this plane towards the y. Okay? So, same thing, our flux, if I can write properly. Excuse me. So our flux is equal to B dot A. So same thing as part A. Our area vector is going to be swooping out along the, or in the XY plane. So we're going to call that phi now. So again, in order to get A parallel to B, that's going to give us a cos phi, which is our B A cos of omega t. So this is the exact same thing we had for part A. So as long as it's rotating at some angular speed, it doesn't matter what axis it's rotating about, you're going to get the same induced EMF. So if we just skip all the extra steps because we already did them, plug them in, our maximum EMF is going to be 0.672 volts. So it doesn't matter which axis you're rotating around, it only matters what angular speed you're rotating.